All right, today we get to do applications of these vector projections, and we're going to do two kinds of applications. We're going to do force and we're going to do work. Okay, what force, here's a picture that you have on your notes. What force is needed to keep this rock from rolling down the hill? So consider a 400-pound rock on a hill with an incline of 30 degrees. If F represents the force exerted by the rock due to gravity, so that goes straight down, and V is the incline, then W1 is the projection of force onto V. So W1 is the projection of force onto V. And the magnitude of W1 is the force required to keep the rock from rolling down the hill. So we're going to follow these steps to find this value. Okay, there's step by step. Step 1, we're going to write F as a vector. All right, so what is F as a vector? In this case, it is 0, -400. Okay, because it doesn't have any x coordinate. It's just going straight down, so that's why it's -400. Step 2, we're going to write a unit vector v in the direction of the hill. Do you remember how you do a unit vector? The unit vector has a magnitude of what? It has magnitude, whoops, it has a magnitude of 1. And in this case, it has an angle of 30 degrees. So our V is going to be 1 times cosine 30 and 1 sine 30. What is cosine 30? Square root of 3 over 2. What is sine of 30? A half. So there's our V. Then step 3, we are going to find W1, which is the projection of F onto V. So we're going to find that with the formula that we have, and that is going to be F, the magnitude of F times V. So that's going to be 0 times square root of 3 over 2 plus -400 times a half divided by the magnitude of V squared. But what is the magnitude of V? It's 1 because it's a unit vector, so we don't even have to really find it. And then we're going to multiply that times V. Okay, so this whole thing becomes -200 times V. And then step 4 is find the magnitude of that, of W1. And so we're going to find the magnitude of W1, which actually just turns out to be -200. Okay, because V, the magnitude of V is 1. So when we multiply it by -200, it just gives us -200. Well, it gives us 200 because not negative, because its magnitude is positive. So 200 pounds is the answer to our question, which was the force that to keep it from rolling down the hill. So let's look at another example using these same steps. All right, number 8. We've got a 150-pound cart sitting on a ramp with an incline of 60 degrees. What force is required to keep the cart from rolling down the ramp? We're going to do exactly the same. We're going to find our force vector, which is 0, negative 150. And we're going to find our unit vector v, which is 1 times cosine 60, 1 sine 60, and that is 1/2 square root of 3 over 2. And then we're going to find the projection of f onto v, which is 0 times 1/2 plus negative 150 times the square root of 3 over 2, divided by the magnitude, which is 1, and we're going to multiply that by v. Okay, so when we do that, when we do all this, we get negative 75 times the square root of 3 times v. So the magnitude of W1 is 75 times the square root of 3 pounds, or if you want to put it in your calculator, 129.9 pounds. That's all we're doing right here. All right, let's try the last one. If you want to turn it off and try it yourself and come back and see if you can get it. Okay, we're going to find our force, which is 0, negative 45. And then our vector is cosine of 12, sine of 12. Now 12 is not an angle that is on our unit circle. So at this point, I'm just going to keep my v vector written like that. At some point, you're just going to have to put that in your calculator and find out what it is. W1 is the projection of f onto v, which is 0 times cosine of 12 plus negative 45 times sine of 12 divided by 1 times v. And if you put this in your calculator, you should get negative 9.36 v. So our magnitude is 9.36 pounds. Right? That's not too bad, right? Let's look at some work problems. Okay, work applications. Another application of vector projections is work done by a force. The work done W by a constant force F acting along the line of motion is the magnitude of the force times the distance traveled, written as work equals the magnitude of the force times the distance traveled, or magnitude of this vector AB. Okay, work, look on the side, work is measured in foot-pounds, the customary system, and joules in the metric system. So that's what we're gonna do. It depends what the problem is. So let's look at number 10. Determine the work done by pushing a 500-pound crate 12 feet. So that would be this little picture up here. We need to find the magnitude of the force and the magnitude or how far it travels. So in this case, that's just going to be 500 times 12, or 6,000 foot-pounds. Okay. So because in this case, the force is just in a line, it would be 500, 0. So the magnitude is just going to be 500, and it goes 12 feet. So let's look at number 11. Determine the work done by a crane lifting a 2,300-pound car 5 feet. Same thing. Work equals 2,300 times 5 equals 11,500 foot-pounds. All right, those are easy enough. If the constant force F is not acting along the line of motion, the work done is given in either of the following forms. So let's look at that. Either in the projection form, the formula is for work is the magnitude of the projection of the force onto AB times the magnitude of AB. Or in dot product form, work is force dot AB. Okay, and there's a little picture there to show all of that. So let's see how we're going to do this. A man, okay, we got 3 problems. A man pushes a car 8 meters with a constant force of 140 newtons at a constant angle of 50 degrees. Use the projection formula to find the work done. So we're going to use this one right here. This is number 12. So in order to do that, we have to find the okay, stick with me. We got, remember that cosine theta equals the projection divided by this. So that means we can rearrange this and say the magnitude of the projection equals cosine theta times the magnitude of force. Our theta is 50 and our force is 140. So we can do this and we're going to get okay, well, I haven't done that yet. We'll just leave that there. So that's this part of it. Oh man, that was this part. And now we need to have the magnitude of AB, which is just how far it goes. And in this case, it goes 8. So our work equals cosine of 50 times 140 times 8. And that equals 719.92 joules. Okay, isn't that fun? Let's look at number 13. A force of 50 pounds exerted at an angle of 75 degrees above the horizontal is required to slide a sofa 20 feet across the floor. Use the dot product formula to find the work done. Okay, the dot product formula is this. So the force, the vector for force is going to be 60 cosine of 75, 60 sine of 75, and the dot product of, or AB is, it's going 20 feet across the floor, so it goes 20, 0 up and down. So we're going to find the dot product of this. So that's just going to be 60 cosine of 75 times 20 plus 60 sine of 75 times 0. So that goes away. So it's just this right here. And when you do that, you should get 310.58 foot-pounds. And we got one more, number 14. Rick is pushing a snowblower with a force of 90 pounds. The handle of the snowblower makes a 60-degree angle. How much work does he do if he pushes the snowblower 15 feet? Okay, I think dot product is easier, so let's use that one. So this is going to be 90 cosine 60, 90 sine 60, and our AB is 15, 0. So when we do that, we get 90 cosine 60 times 15, and that equals 675 foot-pounds. All right, those weren't so bad. So that is the end of the applications for vectors. Okay, we have one short quiz to go over with these dot products and projections, and then the test. And that's it for this chapter of vectors.